talk about physical layer. So physical layer is nothing but controlling my cablings, and then it's all about transferring raw bits on the physical medium, right? So all you do is you need to have cabling, cable connectors and receivers, NIC cards, wireless radios, hubs, switches, routers. It's all your physical layer. It all works on the physical layer, right? And then your protocol data units are bits. Your bits is nothing but physical layer coordinates the functions required to carry bits upstream over the physical medium. As in the layer is in the diagram which you see here, so you get the data from the above layer, which is the data link layer. So that sense it, the physical layer will actually convert the data from your, from your, however it's coming as part of your, how do I say, frames, and break them into digital signatures, which is zeros and ones, right? Your digital signature, which is the digital signature, like the square up and down, or whatever the signal. So that's how it actually converts that into electronic pulses, which will go through the medium, and then the other person at the other layer, with the other physical layer or the receiving end, will actually decode these bits of streams and sends it across to the data link layer. So the physical layer is responsible for movements of individual bits from hop, node to node, which is one point to next point. So, okay, what I want you to do right now is, can you all open your command prompt, do a Windows plus R. You'll see something called as run, right? Okay, so then you type CMD. Once you all get that, type tracert, TRACERT, space, and then type www.google.com and hit enter. Like something like this, right? So what do you see here? You are typing tracert, and then you're saying go and find out google.com. So basically trace the route for me. How am I going through the tracert? So you can type /4 for only IPv4 addresses. That's so that it will be easier for you to understand, or else you will try to see your IPv6 here. So now you are seeing that. Now compare this to this. The physical layer is responsible for moving of individual bits from one hop to other hop. These are the hops which you're seeing here. Each individual hop, right? So my packet or my ping or my tracer says that I need to go to my router, which is this one. Yes, I went to it, and then from here it goes to this route, it goes to this route, it goes to this route, and then it's still waiting for the other routes to go. And that's how we are sending one hop to other hop. So this is also sending stream of bits from the physical layer to the other hops, to the nearest hop, whatever that is. So guys, if you have any questions, raise your hand. If not, then I'll continue. Perfect. Let's move on. So now, its physical layer is pretty simple. So it's just bits. So physical characteristics of physical layer would be representation of bits in zeros and ones, your data rate, your physical topology, and your transmission mode. Like you are doing how do I say, you're doing a full duplex, simplex, multiplex mode is what you will try to look for here, how you're transmitting your data. Moving on. So next is the data link layer. The data link layer is nothing but packages the higher layers into data frames. So you might say, what is a frame? So frames are nothing but so whenever you receive some data from your above layers, it gets chunked or divided into frames. Each frame will be sent across, or this data is broken. The frames is now sent out. Each individual frame is sent out with along with the proper headers and to the next layer, which is the physical layer. For that, it converts into bits and it sends out. So you cannot send bulk of the entire data in one shot. So what the system do, the OSI layer does is it breaks the entire data into small pieces. At data link layer, it's called the frames, and each frame will have something called as a physical destination and physical source and destination address, which is a MAC, media access control. So you said, how do I find out? Let's do IP config. So where is my MAC? Nope, I'm not. So I'll do it /all. So my physical address. This is my physical address. This is my physical address, and this is how it will add it, which was a source who sent out, and it will capture the physical address of that particular NIC where the information was coming out from, right? So you use ipconfig /all, ipconfig /all to figure out what is the physical address of the NIC, network information card network information card on your PC, and what does it hold for. So a tip for you guys, you can actually find out which is the company which made this NIC, or the NIC card basically. So what you do is you can search for something called as NIC identifier, or MAC identifier, MAC identifier. So when you put this MAC identifier in that site, it will identify what is the actual manufacturer who created or who manufactured this particular NIC card. So here I can see Ralink. Again, on the website also it will tell you that this is done by Ralink itself. So MAC address is crucial for you to identify which type of device it came from. So again, just drifting away from the topic, your MAC address will also, if you're investigating where the traffic came from, it will be useful for you to find out if the traffic was coming from a mobile device, from a tablet, from a Mac device, from a Windows device, from a hardware device. So you'll be able to clearly identify which was sending in. Because if you connect your phone to your this thing, you'll be able to find your phone's MAC address as well. And if you search for that, it will clearly say it's a OnePlus 2 or OnePlus, Samsung, Nokia, or whatever that is, Motorola's MAC address. So MAC address has some importance. Don't disregard it as not useful information. Okay. So ipconfig /all will provide you the MAC address, and that's where this frame will add the MAC address of the source and the destination. Right. Okay. So then move on. So most common MAC address is the Ethernet MAC address. That's what I showed you. So what happens at data link layer? So data link layer is divided into two parts, which is logic link control and media access control. Logic link control is nothing but it takes care of the logic control there. The flow control, the error control, deals with protocols, what's coming in, how the protocol should be represented, how it should be converted, how the flow of packets should have happened, of the flow, the frame should happen, when it receives an error, what does it do, how it should resend the frames, and then it takes care of everything else. The media access control does is, it talks to the logical access control and says that, okay, you know what, you give me everything, you pack everything, let me control the actual flow of converting it to sending it to the physical media, right? So data link layer itself has two components. One component talks to the upper layer, tells that, okay, this is what I'm going to do for you. I'll understand, take care of everything. The frames are all pre-built. The source address, the MAC address is all added. Let me now give a flow control as to how the data needs to travel, and error control when these frames are crashed, when an error is received, how do I react about it? The media access control takes that information and actually passes that on, converts that entire data, or helps convert, or helps physical layer understand how can it convert everything into zeros and ones, right? So the protocol data units is frame, as I said, yes. The framing, addressing, error control, flow control. So as I said, the MAC media access control address has got originally unique identifier, which is the company identifier, and the network interface controller, which is the actual address for the MAC control. So this, the other image which I'm trying to point out now will be the information comes from the network layer. The data link layer will add the headers, the frame information, the front and the back, the MAC address, and then it will send out to the physical address. Similarly, on the other part, the packet, when it receives by the actual receiver, the physical layer sends it to the data link layer. It understands, okay, what's the source and what's the destination MAC address, and then it pushes the packet up to the network layer. Okay. Now the network layer. So network layer is responsible for source and destination delivery of packets. So the PDUs or possible data units, protocol data units is nothing but your packets, correct? So network layer actually segments the data in packets so that the data can be transferred based on packet by packet, which is again, breaking the entire data or the amount of information into smaller segments for easier transportation across the network. So network layer ensures that each packet gets from point A to point B, from original to the final destination. But here in the network layer, it will be IP address, right? The network layer is responsible for delivering of information, delivering of individual packets from source to destination host, right? So what the PDUs are, it's called packets. The responsibilities of network layer is addressing the devices and network, populating the routing table and routing, static routes. So what does, you might say, what is routing table? So every router or every system will have a defined set of routing tables, right? So routing table is nothing but it keeps a list of the nearest source and the IP address. Okay, if I am trying to go through a route, or like my router is trying to go through, a particular route, say suppose it will go from my router to the nearest hub. From the nearest hub, it will go to the central hub of the ISP. From there, it will go to actually hit the ISP, and then from there on, it will go to the nearest international ISP, whichever is connecting to my ISP. That route is remembered by the routing in the routing table, so that it quickly identifies and calculates which is the fastest route which it can take to send the data across, right? Then it also, this network layer will also be looking at incoming and queuing of incoming data, and then forwarding it to the constrained service constraint to this packet. So like, if I'm using video, I don't want my video to be lagging, so it means video get higher priority. So it queues data, and based on the priority of that particular service constraint, it will try to forward and cater to that particular protocol or particular to that service, right? So if like we are talking, it's a live streaming, yes, it will get more priority because the quality of services needs to be more higher than email, right? So when you're doing email communication and then you're doing video streaming will take more priority because you will need to have and then your network cable or your network layer will actually take control in terms of sending or ensuring which will get the more priority first and then more bandwidth first. And then it takes care of the internet between two different subnets, delivery of packets to destination with best efforts, providing connection-oriented and connectionless mechanism. So this network layer will be the one where TCP and UDP will come into the picture, right? So yeah, so what happens? The network address is the IP address. The IP address can be unicast, multicast, broadcast, or anycast. Unicast is one destination, one host. Multicast, destined to a group. Broadcast, I'm broadcasting to you all. Anycast, destined to near one. So in this image which you're seeing, so it says every PC is connected to a router, this one here, and it says it actually broadcasts the data here. So it says, I am 168 192.168.1.10. It says 192.168.1.20. And this guy says, hey, you know what, everybody, this is my IP address. I am 192.168.2.10, and this guy is 220. So router will take this broadcast and then broadcast this to these guys, so that these guys will understand, okay, who is connected to my nearest network, and then who can provide me DNS, DHCP, and all this type of typical networking services, right? So broadcast is nothing but, imagine broadcast, you don't understand what broadcast is, simply say it's a public rally. So entire public is listening, but one guy is talking. That's broadcast, right? TV broadcast, radio broadcast. It's only one-way communication. The sender doesn't care about where he's sending information. He will just send out his information to everyone who can listen and capture the data or listen to that particular thing, right? Okay, so guys, I'll stop here for a second, and let me know if you have any questions. Perfect. I get this as no questions. Moving on, the transport layer. The transport layer offers peer-to-peer, end-to-end communication between two processes and remote host, right? Then you have your transport layer as connection-oriented. Connection-oriented is nothing but that particular connection-oriented is nothing but you're trying to ensure that the connection is established, it's not disconnected. The connection is always alive. Like this particular video chat here, or the presentation, or your chats or WhatsApp, right? It's a connection-oriented. The moment the guy goes away, he'll show you'll not see the word online under that particular name. It means the connection is always on, and it's constantly looking out what you're doing, if you're using that application and you're not using that application, right? So the transport layer is responsible for delivery of messages from one process to another. So the protocol suite, the TCP/IP protocol suite is where it comes here. So you have this TCP, which is a connection-oriented protocol, UDP, user datagram protocol, which is connectionless. The TCP can be protocol HTTP, which is 80, nothing but you're browsing the session, or 443, which is more or less saying that, yeah, you want to browse a secure website. And then you have your UDP, which is nothing but your DNS communication on port 53, where it doesn't require to know what is going on. So if you see, the TCP has something called a three-way handshake, right? So before it connects to a destination, it goes through a handshake process, right? So the first time, if I am the sender and you are the receiver, my machine will try to say to your machine that, hey, what? I am trying to connect to you. I'm trying to synchronize with you. So then your machine says, okay, the communication is now coming on port 80. Yes, I'm allowed to accept it. Yes, I am okay to sync with you. And here is my connection, or here is my acknowledgement for your request. Then the receiver, or me, who was the actual initiator, receives that synchronization and acknowledgement request and says that, thank you very much for your acknowledgement. Now this is my acknowledgement for the acknowledgement which you have sent, that I have understood that you are agreed to communicate with me, and from there on, my HTTP request or my communication starts between the sender and the receiver, right? So three-way handshake is the most important thing which you guys will need to understand from a logical standpoint and from a conceptual standpoint, that you need to understand TCP/IP actually goes through a three-way handshake. This will be a common interview question everywhere you go, and this is, and they might ask you a question, why do you think the TCP will go through a three-way handshake? Primary reason, connection oriented. It means the connection has to be established all the time. The sender and receiver needs to ensure that the connection is always established, and so that communication, the data flow can happen even if the session is not active, right? It's a connection-oriented protocol. Similarly, UDP, it's it's like basically saying that, okay, I am not interested in trying to keep the communication with you, but the only thing is I'll do a burst communication. Okay, I have a question, I'll post it and I'll forget it. I'll not even be worried about whether it received by you or not. So let's say suppose your DNS. So if you all know how DNS, domain naming services, actually work, it's nothing but it's trying to query any website. So when you type google.com in your browser, it actually hits your DNS server. So DNS says, I don't understand what is google.com. I need to find the IP address for google.com. And then what it does is, what it does is it's talk to your nearest DNS ISP server and sends the communication to it and just forgets about it. When the receiver receives it and identifies that this is the IP for google.com, it will just send it back. Your DNS server is not worried about connecting to the other DNS server and waiting for his information. Similarly, in this example, you have something called as syslog communication. Syslog communication is mostly used for communication between like a log source, like how would I say that? So it's like a data repository. So every time what you do is, let's say suppose you have your Windows machine and you have some logs on your machine. Like if you're using your system and then you're clicking on something, everything gets recorded. Every network connection you do outside gets recorded, right? So all that information gets stored on your machine. Let's say suppose you want to store it in a remote machine, you will use syslog as your communication channel on port 514. And what happens is it does is, okay, every 1 hour I'll schedule a syslog communication. I'll send out information to the remote server and then forget about it. That's how UDP works. It's not worried about whether the UDP server or the syslog server actually got the information or not, or what was the error or not, right? If he receives the UDP receives an error, it does a retransmission. If not, it completely forgets about it. So a TCP and UDP header will look something like it. Like both TCP and UDP header have got 16-bit of header each. So here you have a 16-bit header, here a 16-bit header, 20 bytes of TCP header, and I think 8 or 5 bytes of UDP. The total size of the UDP header is 5 bytes or something like that. So a UDP header will have multiple parameters or multiple things, which is source port, destination port, sequence numbers, acknowledgement numbers, your data offset, flags, window size, checksum, urgent, and options. So these are all different parameters for the packet to understand where it's coming from, right? Yeah. So what happens is, so when the data actually comes through this particular layer, so it adds the source port, the destination port. In this case, source port can be your machine's port, any number of port, and the destination port can be port number 80 if you're accessing google.com, right? And then look at sequence numbers. Look at the acknowledgement number. The sequence number is because when I say that your data gets divided into different packets, each packet will have a sequence number and then an acknowledgement number as well. And then the rest of the flags of the TCP, saying that it's an urgent flag or it's a sync flag, what type of communication is going on, and it's a window size, like how much long do I think I'll be alive, and the urgency of the packet and the other options. Similarly for TCP, UDP, this is all not required. It will have a source port, destination port, checksum, and the length of the packet itself. And that's pretty much it. It will not add anything else in that because it's not trying to establish a session. So how you can use this? Let me yeah, sorry. So this is Wireshark. Let me open up Wireshark and I'll try to capture some packets. Okay. So this is all the communication which is going on through my machine as of now. So let's say suppose I take a TCP protocol or TCP packet and I want to do a TCP. Oh, not this one. Open this up. I'll open up TCP communication like this one. So now I have a frame. Remember where frame comes from. Where your frame comes from, data link layer, right? It adds the encapsulation. It adds the capture length, the frame length. Then you have your Ethernet, right? Then you have your Ethernet address, which is your MAC address, right? The destination, the source MAC address, right? Then you have the IP protocol, which is an internet protocol. Again, the source IP, destination IP. Where did we talk about source IP and destination IP? We talked about here in the network layer, right? IP address. So you have your IP address here. You have your flags here, right? Reserved bit, do not fragment. It's a whole different thing altogether when you look at a packet. And then you have your source and destination. And then the actual TCP layer is the source port, destination port, port 80, and this one. And the flags of it, right? So sync, reset, push, acknowledge, urgent. So it says an acknowledge. This is an acknowledgement packet because it shows the 1 here, right? My window size. And then window scaling, checksum, and then options, whatever options I have provided here. And then the sequence analysis, sequence flags. So these are all as part of one packet, which you see, just a single packet which is going out there. And that much information you'll capture it by just looking at one packet itself, right? So guys, Wireshark is a beautiful tool which you should try getting your hands dirty with. Install Wireshark on your machine. So this is my HTTP communication. If I just type HTTP there, you'll get it. So, okay, yeah. So this is how my packet looks like. My HTTP packet looks like, right? How do I do it? You know, I'm trying to talk to this particular page at ftp woodson.org, and this is my URL, right? And this is all the content which is going on because this is a HTTPS packet, right? And that's the reason you're not able to see anything here. So how do I say it's HTTPS? Okay. No, it's not HTTPS, but I think it's a sequence packet, which is where the content is garbled or my system cannot understand what the content is. So now I'm looking specifically at port 443 communication. This is all how the 443 communication will look like, a garbled content. You can decrypt it once only if you have a decryption key. It's all encrypted. So, yeah. So that's how you get your TCP header and then your UDP headers, right? So now the responsibilities for transport layer would be service point addressing, connection control, and flow control. So you might say that, you know, how TCP layer actually works, and you know, there are so many things going on. How does it actually does it? So as I said, it does segmentation. TCP transport layer works on the basis of segmenting. Segmenting allows, you know, the traffic from or packets from each of these devices, instant messaging, your multiple web pages, IP telephony, streaming media, to be differentiated in segments. So it will divide your data into different segments, and that segment will get allotted on a bandwidth. Like, okay, if this is the communication channel which is going on, okay, this segment will go now, this segment will go now. It's like a traffic cop, basically traffic cop. Okay, now this side will stop. My right hand side guys will go, and this both left and right hand side will go, and my front and south, north and south guys will go. So that's how the packets get transmitted. They get segmented, and one segments transmit multiple amount of data in one shot itself, right? So that's how, if you see here, every channel as a color. So if you see the purple is here, your red is here, your brown is somewhere here, and green is here. So it means data from our packets from each of the individual applications gets segmented or put on a package get segment, put on a segment, and then that segments get pushed out, and then it does the next layer. So it's basically trying to add in one burst. It's trying to put a lot of different things and send us the burst across. So it's a constant traffic, constant flow of. It's like a traffic cop standing at the junction, saying that okay, now you go, now you go, now you go, now you go, and then it keep controlling it throughout the way. And that's what it uses, is this segmentation of the entire data which comes in. Right? So the how the TCP/IP actually, the whole layered, the whole packets actually work is, as I said in the initial. So when an application and the data gets started from the application layer, it gets the presentation header. So presentation header will add what? It will add the encryption, compression, and the translation of whatever type of medium it's trying to send across. Then the session layer will add its header along with to the current presentation header plus the data itself. Transportation layer will add the what? The source and the destination MAC address along with the current address, the source, session header, the presentation header, and the data. The network header will add the IP address to the current transport header, session header, presentation header, and the data itself. The data link layer will add its header, which is the actual, the flow control, the size of the window, and everything else to the entire length of the headers, and then that gets transmitted into bits on the physical medium, and that gets sent across, right? And when it receives on the other end, everything will try to rip apart every other information. Data link layer will look at this information, take it off. Then it will get pushed up. Network layer will look at the network header information, rips it apart, pushes it up. Transport layer looks at transport header, takes it off, pushes the session header. And that's how the application will layer present the data to you, right? So now let's look at, we have spoken about what is a flow control. So what is all of flow control all about? The flow control is nothing but sender does not flood the receiver, but maximize the throughput, right? How do you do that, right? It's nothing but you, let's say suppose again, traffic cops business. So you are standing in a bus terminal. You have got 1,000 buses. If you allow all the buses to start at once and reach the gate, not one bus will be able to go out. But if you say that the first bus will go at 1 o'clock exactly, and at 1:01, the other bus will go, 1:02, the other bus will go, 1:03, the other bus will go. In between 1:01 and 1:02, 1:0 or whatever the number is, the other bus will come in. So it means you are actually allowing people to come in and go out synchronously, right? This is exactly what happens in the flow control as well. So sender, when I'm trying to, when I am as a sender trying to send more data, the flow control will say that no. The receiver cannot receive this much data. He can only receive this much data. You have to send only this much data, right? So then the sender and the receiver both agree on a standard, the frame of or a standard flow control. Like I can send you this much amount of data so that you can process it, acknowledge it back so that I can send you the next amount of data, right? Yeah. Then the methods of flow control should be start, stop, and wait, or a sliding window. So the first the image you see here is the sender and receiver. The sender, I am sending a data. I'll stop. I'll wait for acknowledgement. When you acknowledge, I'll send it again, and then I'll wait for acknowledgement. It's like stop, and wait. The sliding window is nothing but I will at a given point of time, like 1 to 1.5, I'll keep sending the data. and then I'll stop. I'll wait for your acknowledgement, and then I'll again at 15 to 110, I'll again send the data. Then I'll stop. So as the time window slides or the window is sliding, that's how it will be like this. You will exactly know how much time the data will be transmitted and when you can acknowledge, so that the transmission happens in like burst of information. So that's something called as flow control. So that sender and receiver both have control on how much data the other person is receiving and whether they are able to process it. There is no point me sending more data to the receiver if he cannot process it within the given point of time. Then you have error controls. So error control is nothing but error control. You deliver a frame without an error in proper order of the network layer. So when the frames receive at the destination without any error, it means the network layer worked properly without any. There was no congestion or there is no jam in the network itself. Not too much communication is given by or sent across, or there is no transparent disturbance on the medium itself, right? So remember, if you guys having used their telephones or mobile phones 6, 7, or 8 years back, and then if you are standing right next to the radio, your radio will start interfering with you, right? You can hear the disturbance in your radio frequency. It means there was some disturbance in the signal. Same thing can happen with your network communication as well. If you have too much of electromagnetic interference, or there is a lot of collision, or there is too much amount of noise, or there is too much amount of sudden power outage is there, sudden surge of power is there, the data gets, or the frame gets crashed, and they will receive an error. So error detection is nothing but cyclic redundancy checks or sequence numbers, right? So cyclic redundancy check is nothing but, did I receive the actual packet, or was it supposed to be the actual redundancy check? Did I actually receive it? So other packet will have a redundancy check or checksum value, which will say that, okay, this is a checksum value from the previous packet. Did you get it or not, right? Or the sequence number. So what it does is, the sequence number is again nothing but the series of packets will get received, and every packet will have a sequence number. So when you put all the packets in a sequence, and if you see that there is one packet with a sequence number is missing, you'll request for that packet, or your system will request for that packet, saying that, hey, you know what, the sequence number of this packet or this sequence number was missed. Can you please resend this sequence number? Or you can say acknowledgement and negative acknowledgement. Acknowledgement is nothing but when I receive a packet, or negative acknowledgement is, hey, I never received a packet from you. What is going on? Or else timeout, saying that the connection was not able to set up and I got timed out. Can you please resend the communication again? So these are all the ways where you can do an error detection while sending out and receiving communication. So error recovery can be done by automatic repeat request, is that after a certain point of time, your router or the source or destination will request for a packet and go stop and wait. So that, hey, I never received an acknowledgement from you, or do you think I got it from you? It'll keep asking that question. Can you please send it? Can you please send it? So once it receives it, and then it'll go back and ask it. Go back and selective reject is like, it randomly selectively rejects a packet and saying that, this packet did not meet my criteria. Can you please resend it? So these are all some of the error control mechanisms of error detection and error recovery mechanisms where your protocols will use, or your communication channels will use, ensuring that the communication doesn't stop and this information is passed on as it intended. Right? Okay. Then you have something called as connection-oriented versus connection-less. The connection-oriented, again, telephone system. Even before you are calling, there is a path which is already set up. Like there is telephone routers, or not cell towers which are already set up. It means the nearest cell tower will take your request forward to the next closest to the tower, and the tower will reach out to the destination address, right? Or it receives the main circuit board's circuit switch number, and that will let you know what is the nearest destination's cell tower is, and then it will route the address to it. Connectionless is a postal system because you once you post an address or post a letter, you are not worried about whether it's really reached or not, right? Complete you put the complete address on each letter or each packet, and then the address decides the next hop where to go, right? Um, it again automatically decides, like, should I go to this particular route or this, should I go to this route, whether this is easier for me or that is easier for me, and that's pretty much it. You just have to tell him what to you as a if you drop a post in the post box, you will not tell, hey, you know what, go to this particular post office from there to there. That's how the actual connection based system also works.